Okay, welcome to the class. Okay, let's just start the second class. And okay, here is the what I am telling you. Okay, so we want to integrate a rational function and so we want to integrate a rational function like this. Okay, and if needed, I can perform the long division so that I can convert the rational function into a proper rational function, right? So if needed, sometimes if the degree of the given rational function is less than the degree of the denominator, in other words, if the rational function is from the beginning a proper rational function, then you don't have to perform the long division. But if your rational function is improper, then you need to perform the long division, okay, to convert your improper rational function into the sum of polynomial and proper rational function. Okay. Now, given this proper rational function, the next step is to factor the denominator as far as possible, which means you need to factor qx into a product of linear factors and irreducible quadratic factors. Okay, so when I say irreducible, that means if you factor quadratic factors, then you must consider some complex numbers. So if your quadratic factor cannot be factored within the real coefficients, then such quadratic factor will be called irreducible. And x squared plus 4 is an example of such irreducible quadratic factor. So when you have any polynomial, okay, if say x to the fourth minus 16, then you can always factor such polynomial as a product of linear factors, okay, and quadratic factors. Next, next. Actually, you can skip this one and depending on the type of QX, we will consider slightly different approaches. And there are four different types. Okay? There are four different types. First, case one, the denominator is a product of distinct linear factors. Okay? Like x minus 1 times x plus 1, or x minus 1 times x plus 1 plus x plus 2, something like this. So as a product of distinct linear factors, okay? In such case, okay? In such a case, your proper rational function, so if qx is factored into a product of distinct linear functions, then you can your proper rational function can be always written as a sum of these for some a1, a2, or up to ak. Okay, always. So then a1x plus a b1, a2x plus a b2, up to akx plus a bk, they came from the factoring of the denominator. Then what are a1, a2, or up to ak? those are what you need to find yourself. So in this case, if your qx can be written as a product of distinct linear factors, then your proper rational function Rx over Qx can be written as the sum of these for some A1 up to AK, okay, which you need to find yourself. Okay, so let me give some example. So suppose that I have such integral problem. Now the numerator is second order while the denominator is a cubic order. So my rational function in this case is a proper. So your next step is to factor your denominator into a product of certain linear or quadratic terms. So in this case, x is common. So if I write down this denominator as x times second order polynomial, this second order polynomial can be easily factored into a linear terms like this. So I have three linear factors and they are all distinct, right? Then that means that, so this means okay, so your denominator is factored into a product of three linear terms. That means your integrand x squared plus 2x minus 1 over 2x cubed plus 3x squared minus 2x will be written as a1 over x plus a2 over 2x minus 1 plus a3 over x plus 2 for some a1, a2, a3. Okay, so for some a1, a2, and a3. Okay, then how can I find a1, a2, a3? How? Well, the idea is simple. You just multiply, okay, the denominator into this identity, into this equation, and then compare the coefficients. So the idea to find a1, a2, a3 is simple. You multiply qx, okay, on both sides of the equation, and then compare the coefficients of x cubed, x squared, x, and the constant term. Okay. So in this case, in this case, we don't have any x cubed in the numerator, right? So the numerator is the second order term. So we just compare the coefficients of x squared, x, and 1. Okay. Here's what I'm telling you. So as I said, this proper rational function, when the denominator is split into a product of three distinct linear factors, then it will be always written as the sum of these three types of partial fractions. I mean, those functions are called partial fractions. Okay? Then how can I find a, b, and c? Well, as I said, you multiply qx to both sides. So if what is q? Here is my q. If I multiply q to the left hand side, what do I get? You just get the numerator, x squared plus 2x minus 1. Now, if I multiply qx on the right hand side, what is the q? So my q is x times 2x minus 1 times x plus 2. When this product is multiplied to the first term, then this x in the denominator will be cancelled, right? But since q consists of three linear factors, the other two will survive. So you get a times the product of 2x minus 1 and x plus 2. That would be your first term. Now when qx is multiplied to the second term, in this case 2x minus 1 will be cancelled and you get b times x and x plus 2, right? And when qx is multiplied to the third term, x plus 2 will be cancelled in this case, and the remaining terms, x and 2x minus 1, will be multiplied to c. So that's what you get, right? Now, if I expand, okay, the 2x minus 1 times x plus 2, you get 2x squared plus 3x minus 2 plus, and when x and x plus 2 are multiplied, you get x squared plus 2x. And when x and 2x minus 1 are multiplied, you get 2x squared minus x. Okay. So, if I consider the second order term on the right, if I consider the second order term, the coefficient will be 2a from the first term and b from the second term and 2c from the third term. And the coefficient of x will be 3a from the first term plus 2b from the second term minus c from the third term. And the constant term will be minus 2a from the first term, and from the second and third term there is no constant terms here. Okay, so these are the expressions on the right, and on the left I have x squared whose coefficient is 1 and plus 2x minus 1. So if they are the same, then the coefficient must be the same. So the coefficient of x squared, which is 1 on the left, and that must be the same as 2a plus b plus 2c from the right, right? And the coefficient of x on the left is 2, while on the right I have 3a plus 2b minus c. They must be the same. And the constant term on the left is negative 1, and the constant term on the right is negative 2a. They must match. So here is the equations. So this is 2a. So 2a plus b plus 2c must be 1, and 3a plus 2b minus c must be 2, and minus 2a must be negative 1. So we have these three equations for three unknowns. You can solve these equations, then you will find the values of A, B, and C. So the previous expression can be written, so this, so this will be, let me use this space here. The first term was 1/2 over x plus, b was 1/5 over 2x minus 1 plus minus 1/10 the c over x plus 2 dx. So in other words, we get 1/2 of 1 over x plus 1/5 of 1 over 2x minus 1 minus 1/10 times 1 over x plus 2. We need to integrate this. Now, we can do this in calculation, right? Because 1/2 is just a constant. Now, what do I get if I integrate 1 over x? You get ln x. That's what you get when you integrate 1 over x. So you need to multiply 1/2. Now, in case of 1 over 2x minus 1, which function shall I integrate and differentiate to get 1 over 2x minus 1? Do I have to integrate? Well, 2x minus 1 in the denominator. When that 2x minus 1 is differentiated, you get 2, right? So this one can be written as 1 over 10 times 2 over 2x minus 1, right? Then 2 in the numerator is the derivative of 2x minus 1. So its antiderivative will be ln absolute value of 2x minus 1 multiplied by 1/10. And then I have minus 1/10, and 1 over x plus 2 is integrated to become ln absolute value of x plus 2 plus constant. Okay. So the first case is simple. If the denominator is factored into a product of these linear factors, as in this example 2, then we can just use the natural logarithmic function to integrate each term. The only one thing you need to remember is that if I differentiate ln absolute value of f of x, then you get f prime of x over f of x. So when this is differentiated, right? So if you remember this fact, then I can easily integrate each term. Okay. So, so let me go back to this. So given this problem, first of all, in this case, the degree of the numerator is less than the degree of the denominator, so that it is this is proper rational function. Which means you don't have to perform the long division. So you can go to the next step. You factor the denominator as a product of linear factors and irreducible quadratic factors. Now, in this case, your denominator is split into the product of distinct linear factors, right? So these are all distinct linear factors. In that case, you need to put this rational function as the sum of those three partial fractions. Okay? And how can I find A1, A2, A3 or A, B, C? You need to multiply the denominator on both sides. Okay? And when you get this, you expand them and you just compare the coefficients of the second order term, x squared or x, and constants. So you need to solve these three equations in three unknowns. You can find this, right? You can easily solve this algebraic problem. So you can find A1, A, B, and C, and then you use this formula. The derivative of ln f of x will be f prime over f. So if we use this, we can easily integrate the rational function of the first case. Now, second case, what if the denominator is factored into linear factors, but some linear factor is repeated? For example, some factor is repeated r times. In other words, when you factor your denominator, qx is a product of a1x plus b1 to the rth power. If such term exists, then this a1x plus b1 to the r, that will introduce these r terms, sum of r partial fractions. Now, okay, so a1x plus b1 to the r will introduce, that one introduces these r terms. And note that the numerators are all constants. Okay, but the denominator will be the polynomial of degree 1, 2, 3 up to r. So the degree of the denominator will increase from 1, 2 up to r, while the numerators are always constants. You never increase the degree of the numerators. Okay, numerators will be always numbers, constants, but denominators will be a1x plus b1, a1x plus b1 squared, a1x plus b1 cubed, and so on. So let me give some example. Okay, so suppose that I have this cubic power polynomial in the numerator and fifth order polynomial in the denominator. So I have a proper rational function. So you don't perform the long division. Now, when I look at the denominator, x is repeated 2 times and x minus 1 is repeated 3 times. So this x squared, okay, this x squared will introduce two terms, a over x and b over x squared. You never increase the degree of the numerator. Numerators will be just numbers a and b, while denominator is x squared. Then this x minus 1 is repeated 3 times. In that case, that term, this single x minus 1 cubed, will introduce 3 terms. Some number over x minus 1, another number over x minus 1 squared, and another number over x minus 1 cubed. Then how can I find a, b, c, d, and e? You multiply the denominator, okay, on both sides. So if I multiply this x squared times x minus 1 cubed on the left hand side, on the left I have x cubed minus x plus 1. On the right, if I multiply this term, okay, then first in 1x will be cancelled when the first term is considered, so you get a times 1x remains, and we still have x minus 1 cubed plus, when I multiply the x squared and x minus 1 cubed on the second term, in this case x squared will cancel out, so you get b times x minus 1 cubed. Okay, now when the denominator is multiplied on the third term, we get c times, and no cancellation with x squared, but 1x minus 1 is erased, but I still have 2 more x minus 1. And then when denominator is multiplied on the fourth term, you get d times x squared times x minus 1. And when the fifth term is considered, you get e x squared. That's it, right? Then you need to expand each term on the right. So you get a times, when x minus 1 is cubed, you get x cubed. But since I has 1 more x, you get x to the fourth minus 3x cubed plus 3x squared minus 1 times x plus b times x cubed minus the 3x plus the 3x minus 1. Then c times x to the fourth minus 2x cubed plus x squared plus dx cubed minus x squared plus ex squared is obtained. Okay, and then if I consider x to the fourth, then the coefficient will be a from the first term and c from the third term. And in case of x cubed, I have negative 3a plus the b, minus 2c plus the x cubed plus, in case of x squared, I have 3a minus 3b plus c minus the d plus ex squared plus minus a plus 3b x, and the constant term is minus b. That's it, right? So that must match x cubed minus x plus 1. So that means A plus C must be 0 because there is no counterpart on the left hand side. And negative 3A plus B minus 2C plus D must be 1. And there is no the square term on the left. So 3A minus 3B plus C minus D plus E must be 0 as well. And negative A plus 3B must be negative 1. And negative B must be plus 1. So you need to solve these 5 equations in 5 unknowns. Then you can find A, B, C, D, and E. Right? Right? And then you can integrate each term. Okay? Now, then how can I integrate this? Okay, so let me make some more space. Okay, then so suppose that you find the values of A, B, C, D, and E. Now, if I integrate both sides, then, and assuming that you know the values of A, B, C, D, and E, right? The first term, 1 over x, what do I get if I integrate that term? You get ln absolute value of x times A is obtained, right? And B over x squared, then that is B times x to the negative half power. Which function shall I differentiate to get this as the derivative? You get B times x to the negative 1 with minus coefficient. Then when you differentiate that function, you get B over x squared with a positive sign. And from the third term, C over x minus 1, if you integrate that term, you get C times ln absolute value of x minus 1. And for the next term, similarly, you get d times negative d times x minus 1 to the negative 1, right? And the fifth term, that is e times x minus 1 to the negative third power. So to get as the derivative, you must differentiate e times x minus 1 to the negative half with minus 1 half in front. Then when minus 2 is multiplied, that minus 2 times negative 1 half will give you plus 1, and you need to decrease the power by 1, then you get x minus 1 to the negative third power, which is 1 over x minus 1 cubed. So this will be your result, right? So your task, it will be probably to identify these numbers A, B, C, D, and E, and then do the math, right? So this is how you integrate the second type. So let us consider another example. So suppose that I have such very lengthy expression, okay, and I want to integrate by some reason. Then, since the numerator is fourth order polynomial while the denominator is only a cubic order polynomial, we have improper rational function. So we need to consider the long division. So given x to the fourth minus 2x squared plus 4x plus 1, if I divide this by x cubed minus x squared minus x plus 1, first I compare x cubed and x to the fourth to get x. Then we get x to the fourth minus x cubed minus x squared plus x. So if I subtract this from the given expression, then you get x cubed and minus x squared plus the 3x plus 1. And then if I consider 1, then you get x cubed minus x squared minus x plus 1. So if I subtract this expression below, then you get 4x. So, so that means this expression in the numerator can be written as x plus 1 times denominator plus 4x. So the integrand can be written as this new polynomial plus so this polynomial plus proper rational function. The integration of the polynomial is simple, right? So integration of x plus 1 is simple. You get just 1/2 of x squared plus x, right? Of course, plus some integral constant, okay? But now what matters will be the integration of the proper integral, proper rational function. So what is the next step? You need to split the denominator. So when you consider the factorization of the denominator, you get this expression. This is a high school math, though probably you can do this calculation yourself. So if you factor this cubic polynomial, then you get x minus 1 squared times x plus 1, right? Now you can use this approach as in the slide, or you probably learn some different techniques from your high school days. So anyway, somehow you could factor this denominator, then we get this 4x over qx will be written as the sum of partial fractions. Now since the denominator has two copies of x minus 1 and x plus 1, x minus 1 will introduce these two terms, while x plus 1 will generate the third one. So this is what we have. Now, what is the next step? You multiply the denominator on both sides. So when this term is multiplied on the left hand side, you get the numerator only. On the right hand side, when the first term is multiplied by the denominator, you cancel 1x minus 1, but you still have x minus 1 more, and then x plus 1. And this denominator is multiplied to the second term, you get b times x plus 1. And the denominator is multiplied to the third term, you get c times x minus 1 squared. So you get a times x squared minus 1 from the first term plus b times x plus 1 and c times x squared minus 2x plus 1. So you get a plus c x squared plus b minus 2c times x plus minus a plus b plus c as the constant. And that must be the same as 4x. So the coefficient of a plus c must be 0 because there is no x squared on the left. And b minus 2c must be 4. And negative a plus b plus c must be 0 because the constant term does not exist on the left. So if you solve this three equations in three unknowns, you can find the values of a, b, and c. So my original problem can be written as the integration of this simple polynomial plus the sum of these three partial fractions. Okay. Now, as I said, x plus 1 can be easily integrated 1 over x minus 1 can be integrated to become ln, absolute value of x minus 1, and 1 over x minus 1 squared, that is integrated to become negative 1 over x minus 1, and you can just multiply 2. And then the minus 1 over x plus 1 is integrated to become ln x plus 1. Okay, so the second case is quite simple. Right? So I just need to integrate. I need to use the integral integration of a polynomial, which is quite simple, and then you need to integrate the linear factors. And for the integration of the linear factor, if you differentiate, say, ax plus ln ax plus a b type function, you get a over ax plus b. So that's what I need for the integration of this or this type of a function. So 1 over x minus 1 or 1 over x plus 1 for these two types, what I need is only this one, right? So case 1 and case 2 will be quite simple. The problem becomes a little bit complicated when the denominator q contains a irreducible quadratic factor. Okay. And whenever your if your qx has ax squared plus bx plus c, such irreducible the quadratic factor, but if you have only just one copy, I mean, if this quadratic factor is not repeated, okay, so here it qx, so case 3 considers the following: qx contains irreducible quadratic factor, but they are not repeated, they just appear on only once. Okay, so it is not repeated. In that case, each quadratic factor will introduce this term. Okay, so here the linear term over quadratic term in the denominator. So your task will be to identify these unknowns a and b. Okay, so these a and b are the numbers to be determined. Then how can I find the values of a and b? The idea is simple. Idea is the same. You just multiply the denominator. So let me give some example. So for example, suppose that I have this rational function f defined by x over x minus 2, a linear factor, but x squared plus 1 and x squared plus 4. In that case, x minus 2, the linear factor, will introduce, as in case 1, some number over x minus 2. Now, in case of x squared plus 1, that is repeated only once. That term appears once. So that will introduce a linear term, bx plus c over x squared plus 1. Now, the third term of this factorization is x squared plus 4, which is also quadratic. And that term will introduce this dx plus e, a linear term over x squared plus 4. So we get this expression. Then you can multiply the qx on both sides. So when qx, please note that this is your qx. So when qx is multiplied on the left, you get oops. So when qx is multiplied on the left, you get just x. And when qx is multiplied on the first term on the right, you get a times x squared plus 1 times x squared plus 4 plus bx plus c times x minus 2 times x squared plus 4. And then dx plus e times x minus 2 x squared plus 1. Okay? And then you arrange these, expand these terms and compare the coefficients to determine A, B, C, D, and E. Okay? So you can find this. Then, okay, so suppose that somehow I could identify these values, A, B up to E. Okay? Then what's next? I need to integrate each term on the right, right? So probably you want to integrate these terms on the right. So the next step is to integrate each term. Okay, then when I integrate the first term, it is simple, right? I did this multiple times now. Now, add in absolute value of x minus 2 with the value a, right? Then, what do I get when I integrate the second term? So, suppose that I know the values of b and c, okay? Then, what do I get when bx plus c over x squared plus 1? What do I get? Well, well, if I consider the ln x squared plus 1 function, when I differentiate this, what do I get? You get 2x over x squared plus 1, right? So, okay, so then probably I can rewrite this as 2x over x squared plus 1 times b over 2 will give you the first term, bx over x squared plus c. Plus, I have c times 1 over x squared plus 1 dx. So when I rewrite bx plus c over x squared plus 1 by the sum of these two, then the first term will be b over 2 times ln absolute value of x squared plus 1 is obtained, right? Then what is the second term? What do I get if I integrate x squared plus 1? You get arctangent, right? Plus some constant from the integration. That's what you will get, right? And you get the same similar result from the integration of the third term. Okay, so I have, yeah, let me erase this, and then so When you integrate this term, you get arctangent. So this is the formula we need to use, okay? And since it is 11:20, so let's call it a day here, and then let me continue on Wednesday, okay? But for the third and fourth case, I might need this formula number 10, okay? So please review this idea, and then let me continue from this slide on Wednesday. Thank you for listening, and see you on Wednesday.